Hi, so today we discuss the last topic from game theory course, and this topic is evolutionary games. So you remember at the very beginning of this course in October, we started with discussing key assumptions of strategic games. And one of these assumptions was perfect rationality of players. So we assume that all the players are able to analyze the game successfully. They know their payoffs, they know the payoffs of other players, and they design their strategies in the way enabling them to achieve maximum possible payoff. However, this is kind of a questionable assumption because, optimization process is very costly. I mean, in terms of cognitive effort, and on daily basis, outside the game theory class, we often behave not in line with optimization strategy but in line with heuristic strategy. So we just have some patterns of behavior, interaction, and decision making, and we follow these patterns. So we do not analyze whether this pattern is good or bad. This is just our strategy. It's not entirely efficient, not always. Nevertheless, it's definitely much more time saving and cognitive effort saving. And actually, there are a lot of studies in behavioral economics, so probably this is the core of behavioral economics, which analyze how real life behavior of people is different from what is predicted by neoclassical economic models, which rely on this principle of self-optimization, just like conventional game theory. So in this case, it's really questionable whether we can apply the tools of game theoretical analysis to analyzing, social interaction, decision making, and strategic games in real life. So in this case, what we can do is to combine conventional game theory tools with evolutionary biology, because evolutionary biology works in a very similar principle as heuristic strategy. So without, attempting to identify optimal payoff and strategy of achieving this payoff, we just choose some strategy and then we check whether it's successful or not successful. So if it's successful, then we take this into account and use this strategy in the future. And if it's not, then we forget about this strategy and we elaborate on another strategy. So actually, this is how evolution works. There is no single part in your body which would be subject of explicit design. Like no one ever sat down and tried to design the perfect human body. Instead, you just have some features, like let's say it in a different way. We just have the genotype which survived in the process of evolutionary selection. Like, 1 million years ago, there was, an individual with brain bigger than it used to be before as the result of genetic mutation. It turned out to be a good and efficient feature, and that's why nowadays we also have bigger brain than our ancestors. Again, this is how it works. So the key of evolutionary process is that, in a different way. So there are two components of evolutionary process: generator of variety and test. Genetic mutations work as generator of variety. So this is completely random process. Again, as I said before, it's not the result of some optimizing design. So it just happens, and if this new feature is useful, appropriate, and efficient, then it stays. If it's not, then, individuals with this feature just die out and they do not reproduce, and this is what we call evolutionary selection. So again, there are three key principles, which are heterogeneity, another name for variety, because this is the idea. In order to select some features, you have to have the variety of features. Fitness, which is measured in terms of reproductive success. So, if this is good and efficient, then there is a higher chance for reproduction, and then this feature will be reinforced. Or let's say this genotype will stay, let's say, in population. And selection. And selection is actually when we apply game theory. If some feature is characterized by high fitness, then again, individuals characterized by this feature will reproduce, and we will see the process of positive selection. And actually, that's why the framework of evolutionary biology is more suitable for analyzing real-life human decision-making, cooperation, and interaction process. So we do not design our strategies keeping in mind, some maximum possible payoff. We do not attempt to optimize. Instead, we just select some strategy, and then we check if it's good, if it results in the desirable outcome, or let's say outcome which is good enough, which is appropriate for us, then we use the strategy in the future. If it's not good enough, then we reject it, we do not use it in the future. So in this case, we observe negative selection. Okay, I'm pretty sure about positive selection, but okay, probably you can use this term safely. So we can interpret genotype as a particular pattern of behavior called behavioral phenotype. As I mentioned before, some types of behavior are more suitable. It means that players who, pursue these types of behavior have higher reproductive success, and we call this fitness. Players with fitter genotype reproduce more successfully and become more numerous, which means that their proportion in population increases, and this is called selection. Mutation, again, as I mentioned before, serves as the random generator of variety. We assume that mutant genes can invade the population. You will see it in a second. And population is called evolutionary stable if its current configuration, like let's say according to the types of players and combination of genotypes, successfully prevents from invasion. So if we have evolutionary stable population and it consists of the players with single behavioral phenotype, then we deal with monomorphism. And if there are several types of players existing within the same population, then we deal with polymorphism. So we assume that strategy can be interpreted as behavior of phenotype, and reproductive fitness can be assessed through the payoffs. So which means that players with higher payoffs will have higher reproductive fitness, because they will have more resources, opportunities, and so on and so forth. So I believe this is kind of intuitive. So we can start with a simple prisoner's dilemma. And again, as I said before, instead of attempting to identify the most optimal strategy for each player, we will just assume that there are two players who pursue different types of strategies. I meant two different types of players which pursue two types of strategies. So we have defectors who always defect and cooperators who always cooperate. And we assume that proportion of cooperators is equal to X. So in this case, we can calculate the expected payoff of cooperators. So if you always cooperate, then your expected payoff is equal to 100 times probability of meeting another cooperator plus 10 times probability of meeting another defector. If you are a defector, then your expected payoff is equal to 20 times probability of meeting cooperator plus 40 times probability of meeting another defector. Okay, so in this case, it's easy to see that defectors will have higher payoff in comparison to cooperators for all the possible values of x. And since this is a proportion, those possible values are between 0 and 1. So this implies that defectors have higher fitness in comparison to cooperators. So if we assume that Prisoner's Dilemma is played for only one round, then we shall expect a population consisting only of defectors. Because as I said before, based on the values of expected payoffs for defectors and cooperators, we see that expected payoff for defector is higher, regardless of the ratio of cooperators in the population. Okay, let's do another thing. Let's assume that this game is played for 2 rounds. And in this case, instead of agents who always cooperate, we deal with agents who play tit for tat. So let's say TFT type of players. Tit for tatters. Okay, whatever, you've got the idea. So as you remember, tit for tat is a kind of strategy which just replicates the last movement of the opponent. So if your opponent cooperated in the last round, you cooperate as well. If he decided to defect, then in this round you defect as well. So in this case, if 2 agents playing tit for tat cooperate, let's say interact, play this game, that each of them will get 200 because we assume that they start with cooperation and neither of them will give any reason to defect to the other player. So in this case, we have 200, 200. If we have 2 defectors, then each of them will get 40. If tit for tat player interacts with defector, then tit for tat player will get 10. Again, it follows from this table in 1 round. Then this player will defect as well, so we have to add 40. As the result, we have 50. Defector will get 200 in the initial round, and then defector gets 40. So that's why we have this payoff 50, 240, and 240 and 50 in this case. So analogously, we can do the same kind of calculations for defectors and TFT player, assuming that proportion of TFT players in population is equal to X. And again, when you compare those expected payoffs, you will see that payoff of defector is higher than expected payoff of TFT player for all the possible values of X. So again, in this case, we can assume that defectors have higher fitness than TFT players, and TFT players cannot invite defectors. So population consisting only of defectors will be evolutionary stable. Now, assume that this game is played for 3 rounds, and now it's gonna be more interesting. So again, if 2 TFT players interact, then each of them will get 300, like basically 100 times 3 rounds. Defectors will get 40 times 3, 120. In this case, again, if tit for tat player interacts with defector, then tit for tat player will get another 40 and defector will get another 40, which will result in this payoff. Okay, so once again, we can calculate the expected payoffs of TFT players and defectors. So the first one will stand for expected payoff of TFT player. So 300 times probability of meeting another TFT player plus 90 times probability of meeting a defector. Analogously for defector, 280 times probability of meeting TFT player plus 120 times probability of meeting another defector. So now when you compare those payoffs, you will see that defectors have higher fitness higher expected payoff in comparison to TFT players only if proportion of TFT players is smaller than 60%. So if more than 60% of population is of TFT type, then TFT type, I wanted to say has an advantage, then I changed to is fitter, and as the result there is some strange mixture. Okay, once again, if more than 60% of population is TFT type, then TFT type is fitter. Because if X is bigger than 0.6, then TFT players have higher expected payoff and fitness correspondingly in comparison to defectors. Vice versa, if less than 60% of population is TFT type, then D type is fitter, which was calculated based on this inequality. Because, again, if X is smaller than 0.6, then expected payoff of defector is higher than expected payoff of TFT player. And finally, if TFT players constitute exactly 60% of population, then we deal with polymorphism. So in this case, we have evolutionary stable population with 60% of TFT players and 40% of defectors. Because if X is equal to 0.6, then those two players have the same expected payoffs and they have equal fitness. Okay, we can represent this graphically based on those formulas for the different values of X. So again, minimum value is 0, maximum value is 1. So when it comes to TFT players, minimum possible payoff is equal to 90 in case there are no TFT players. There are no other TFT player in the population. And maximum is equal to 300, which occurs when all the players in the population are of TFT type. Analogously, you do the same calculation for D-type players, for defectors. Okay, so this is just a graphical illustration of how we identify, this point of stability. This is not actually a point of stability because, let's say, there is no reason for us to expect any changes in population if the proportion of TFT players is equal exactly to 60%. Because let's say if TFT players constitute less than 60% of population, then D-type players, defectors, will be fitter, and if they are fitter, we expect the proportion to increase. And vice versa. And actually, when we have exactly 0.6, then there are no reason to expect increase in the number of D or TFT type players. So at this point we can go further and assume a known number of rounds, let's say n rounds. So the idea is like this. As you noticed before, tit-for-tat strategy does not really pay off in short-run perspective. So if prisoner's dilemma is repeated, for 1 round or 2 rounds, then defectors will always have higher fitness because they will have higher expected payoff, as we mentioned before. So actually in this case, we can analyze, let's say, the optimal number of rounds in order to maintain sufficient proportion of TFT players in the population. Okay, you will see this. So analogously to what we did before, let's assume that proportion of TFT players in population is equal to X, and the game is played for n rounds. So if defector plays with defector, then we always have 40 times n rounds. If tit-for-tat player plays with defector, then TFT player gets 10 in the first round, and then 40 in the rest of rounds. That's why we multiply by n minus 1. And if defector plays with TFT player, then he gets 200 in the first round and then 40 in each subsequent round. And now just will be calculated in this way. And if TFT player plays with TFT player, then each of them will get 100 in each round. That's why we just multiply 100 by n. Okay, so this is how you calculate this. You can open the brackets and simplify this a bit. So this is what you should get at the final result. So again, in this table, I just wanted to present you the idea of how you calculate those expected payoffs. And here you have everything calculated. I mean, brackets opened and so on and so forth. So this is how it looks. So using this table and keeping in mind that proportion of TFT players is equal to x, we calculate the expected payoff of defector. So 40n times 1 minus x, probability of meeting defector, plus 160 plus 40n times x, probability of meeting TFT player. For TFT player, we have 100n times x plus 40n minus 30 times 1 minus x, probability of meeting a defector. So now, knowing that we have n rounds, we will try to figure out the condition So we can figure out the condition under which TFT players will have higher fitness. Okay, so in this case, it will be enough to figure out the condition under which TFT players have higher expected payoff. Because as I mentioned before, if some player has higher expected payoff, it means that this player has more resources, higher reproductive success, and we should expect that proportion of players of this type will increase in the population. That's why if one of the players have higher expected payoff than another player, then this is not really evolutionary stable. So for instance, if we know that defectors have higher expected payoff, then the number of defectors will increase and number of TFT players will decrease. So now we want to figure out the condition under which there will be more TFT players in the future in the population. And in order to do so, we have to calculate the value of x under which TFT players will have higher payoff and higher fitness in comparison to defectors. And here you can see this. So this is expected payoff of TFT player. This is expected payoff of defector. If you calculate everything, you get this answer. So x should be bigger than 30 over 60n minus 130. Actually, we can check this. So as you remember, when we assumed that game is played for 3 rounds, we calculated proportion of x, like critical proportion of x, as 0.6. And again, we have 30 divided by 180 minus 130, so we have 30 over 50, and this gives you 0.6. So calculations are fine this time. And yeah. So again, if proportion of TFT players is bigger than this value, then expected payoff of the random TFT player will be bigger than expected payoff of random defector. TFT players will get an advantage. They will have bigger evolutionary fitness. And as the result, number of TFT players will be instantly increasing until we have a population consisting of TFT players solely. This is the idea. Again, I would like to reinforce it one more final time. If any player has higher expected payoff, then this player has more resources. Then this player has higher reproductive success, and in the future, the proportion of players of this type will increase. In our case, actually, it will increase infinitely. Not infinitely, until it reaches 100%, because this game is relatively simple. So, we just have one point at which polymorphism is possible. If proportion is smaller than what we have here, then we have only defectors. If it's bigger, then we have only TFT players. So once you leave this point, there is no way to maintain polymorphic population and evolutionary stable equilibrium. Okay. So chicken game might be another useful abstraction to analyze evolutionary games. So in this case, we have M-types players and W-type players. So M stands for macho in original model, W stands for wimp, and I'm too uncomfortable with repeating these words numerous times. That's why let's stick to W-type and M-type players. So M-type players always go straight, and W-type players always swerve in this case. Okay, so assume that proportion of M players in population is equal to X. So in this case, we can calculate the expected payoff of the W-type player, like 0 times 1 minus X, probability of meeting another W-type player, minus 1 times X, which gives you negative X. And for M player, expected payoff is equal to 1 times 1 minus X minus 2 times X, because X stands for the proportion of M players in population. And as a result, we have 1 minus 3X. So basically, if you equalize those two payoffs, you will get the critical value of 0.5. And if X is less than 0.5, then M-type players are fitter and their proportion will increase. And if X is bigger than 0.5, so proportion of matches in population exceeds 50%, then W-type players are fitter and their proportion will increase. And actually this makes sense, because take a look, if we have population consisting of only M-type player, then each time, because they go only straight, they will lose their payoff, like -2 over and over again, and definitely this is not good for evolutionary fitness. So what we can do in this case is to represent this graphically. So maximum possible payoff of W-type player is 0, and in the worst case scenario we have -1. Okay, actually you can see it on the graph. Okay, ta-da, here we have it. So for W-type players, the maximum possible payoff is 0, worst case scenario is -1. So W-type player never goes straight. That's why it can either play with M-type player and swerve and then get 0, or get -1. Oh, sorry. It can either W-type player can either play with another W-type player when both swerve, and then this player will get 0, or he can play whatever with M-type player. Then again the payoff will be -1, because this is the idea. When W plays with M, the payoff of W is -1. For M-type players, if this player plays with the W-type player, then maximum possible payoff is equal to 1, and if he plays with another M-type player, then payoff is -2. And here we have the proportion of M-type players in the population. And accordingly, the expected payoff depends on this proportion. Like basically those functions we already calculated before. So we have equilibrium on the intercept, it's equal to 0.5, and in this case it's a bit different. So in case of prisoner's dilemma, it was like this. Once you leave this point, there is no way to get back. Like if you have value of tit for tat players less than 0.6, then defectors will prevail. If you have proportion of TFT players bigger than 0.6, then TFT players will prevail. So this is like one single point of stability in this case. And once you leave it, there is no way to get back. In this time, it's a bit different. Because, if you have proportion of M-type players bigger than 0.5, then W-type players will get an advantage, and they will have it until the number of players in the population equalizes. And the opposite, if you have number of W-type players bigger, then M-type players have an advantage, and their number will increase until we reach, this golden middle of equilibrium. So yeah, if we suppose that population consists of M-type players only, once W-type players will invade, like they will, basically there will be W-type players in this population. This is what we call invasion. Their proportion will increase up to 0.5. And the opposite, if population is dominated by W-type players, once M-type players invade, the proportion will increase up to 0.5. And actually you can verify this, it just follows the idea behind these calculations and this graph as well. Like there is nothing except this simple algebraic intuition. And interesting enough, in this game, evolutionary stable outcome is identical to Nash equilibrium in mixed strategies. When both players choose swerve or straight with probability of 0.5. This is a bit different because we have players who choose only swerve and straight, and their proportions are equal to 0.5, but the outcome is pretty the same. So instead of having two players choosing their strategy randomly with probability 50%, we have 50% of population choosing each strategy. Okay, probably I paid too much attention to this. Okay, so keeping this in mind, we can analyze some generalized hawk-dove game. And this game is about competition for resources. So Hawk's strategy is always aggressive. He fights in order to try to get the whole resource of the value of V. Probably, yeah. The dove strategy is to offer to share and avoid fighting. So when two hawks meet each other, they fight. And they have equal probability of getting the resource, so the expected value is the value of resource divided by 2. And the probability of losing is the same, and the cost associated with losing the fight for resource is negative C. So the expected payoff for each is V minus C over 2. And when two doves meet, they split resources in equal shares without fight and associated losses. So this is how payoff metric looks like. So it's easy to identify that if reward for resource exceeds cost of fight, we deal with prisoner's dilemma, because in this case this game will just have prisoner's dilemma structure. And then and if the value of resource is smaller than cost associated with fight, then we deal with chicken game. So again, you can just verify this, and if you keep in mind the structure of PD and chicken game, it should be kind of intuitive. Okay, so if we take the case when value of the resource exceeds the cost associated with fighting for this resource, so we take bigger value than C, we can try to figure out evolutionary stable outcome under this condition. So we can suppose that proportion of doves is equal to D, and then proportion of hawks is equal to 1 minus D. So this is the equation for expected payoff or fitness of H-type players. So we have 1 minus d, probability of meeting another H-type player, times times the value of payoff associated with this interaction, plus probability of meeting D-type player, small d, times the value of the resource. And for doves, it will be pretty similar. So if they meet H-type player, they get 0, and probability of meeting H-type player is 1 minus d. And if they meet another D-type player, then both get V over 2. And probability of this is equal to d. Okay, so if you compare those, it's easy to detect that for all these, I mean for any proportion of D-type players in the population, H-type players have higher expected payoff. So they have higher fitness, they are evolutionary stable, and population is likely to be monomorphic, which means that since hawks have an advantage, their number will increase instantly until it reaches 100. Sad but true. In contrast, when we deal with the chicken game, analogously we can assume that value of the resource is smaller than the cost associated with fight for this resource. And analogously, if we assume that proportion of doves is equal to d and proportion of hawks is equal to 1 minus d, then if you compare expected payoffs of hawks and doves, now assuming that v is smaller than c, then we can have stable and polymorphic population if the proportion of D-type players in population is less than 1 minus c over v. So in this case, it is possible. Otherwise, population will be likely to be monochromic. In terms, we will see either doves or hawks prevailing in this population. Okay, I really hope it was fine. I mean, not too complicated. And as I said before, this is the last lecture, the last piece of theoretical material you need to know in order to pass the exam. Okay, so thank you for watching.